In this video, I thought we'd play a little bit with a circle inversion. So you can sort of map a point that's inside a circle to one that's outside a circle by O here represents the origin. This is Wikipedia. So you have this sort of radial line going out from the origin. And if you had a point P that was inside the circle, then you can map it to a point P prime that's outside the circle, and they will be along the same radius from the origin, but with this sort of the two radii, the two lengths from the origin being equal to the radius squared of the circle that you are using for the purposes of reflecting. And people will often take that to be a unit circle. That doesn't have to be. So that's the sort of thing we're doing, and you can make lots of elaborate drawings. I'm going to sort of keep it simple. And so here is this picture of, sort of petals, a picture you can make with a compass. I've been making this since I was a kid. Sort of take your compass and draw a circle, and then you put your compass somewhere on the circle, and with the same setting, you just start drawing arcs, and you can make this sort of flower, petal, hex sign, mandala, whatever you want to call it, drawing. So that was my starting point. And then I just took one of these arcs and drew it here. And then I asked myself, so this arc is inside the circle, so what is its, if I invert it, what is it? And simply you could say, I'll do it simple and then I'll go more elaborate, but the points that are on the circle, not inside the circle, but on the circle, map to themselves, because it's, you're mapping from along the same radial line, and you want the distance from the origin to the point and the new point, that product, to be r squared. Well, if you're on the circle, then the p and the p prime are the same. So this point will map to itself, and that point over there will map to itself. And this point down here, since this arc goes through the origin, then that point gets mapped to infinity. And so then if you sort of take a point sort of very close to the origin down here and take some radial line, and so I need this, what it turns out to be is that this is going to be sort of a horizontal line, that circles and parts of circles map to other circles, but this point is going to map to infinity, so that suggests this this line that this maps to must go off to infinity, or it's a horizontal line on this side and horizontal line on that side. And so you can just, working with those 3 points, and if you're familiar with circle inversion, then you sort of know, like, those 3 points will determine it and tell you what happens. But I'm a glutton for punishment, so I decided to take an arbitrary point along the arc, and does it really end up on the horizontal line? Okay, so I just, in SVG, I drew this picture for myself, and let me add to it here. So I just took a snip of it, and I'm going to call this angle here theta, because it's easy for me, if, like, this is my real origin that I'm of interest, but I can understand this arc using this as the radius, and I'm working with a unit circle. So if that is theta, then I can say that from here to here, say, is cosine of theta. And from there to there is sine of theta. And so that point there is sort of sine, it's a terrible S, sine of theta. And then in back to this origin, the x's, they agree on the x's, but the y's change, and it'd be 1 minus cosine of theta. So that is an arbitrary point, a point parameterized by that theta along the arc. And then I'm going to switch over to Mathematica and let it do some of the math for me. So I said x1 I called it because this is my first point. X1 is sine of some theta, and y1 is 1 minus cosine of some theta. And I want to get a radius, and so that's x squared plus y squared. And I've got, when I square this, I'm going to have sine squared, and when I sine that, I'm going to, among other things, I'm going to have cosine squared, and then there's a trig identity. So I said the radius was the square root of x squared plus y squared, and I asked it to be simplified. So it's just doing a bit of trig for me. I don't know what I did there, but there is x1 is sine of theta, y1 is 1 minus cosine theta, and if I simplify, that ends up to be square root of 2 minus 2 cosine theta. Now, the circle inverting process is for my new point. I want a radius that is working with a unit circle. So 1 on this, 1 on R2 is 1 on R1 because I'm working with the unit circle here. So that just inverted that. Okay. And now I'm looking for the x2. Okay. So my original x divided by my original r, that works sort of as a cosine, as taking the horizontal component. So I am taking x on r, that's sort of a cosine, and then I'm multiplying it by my new radius. And I'm getting that it's 1/2 the cotangent of theta on 2, so it did a lot of algebra for me, some trigonometry, some algebra, and it came up with that. And you can sort of play the game that I can relate this, relate these values, the cosine and the sine, and get tangents and cotangents and do all sorts of trig identities. And Mathematica knows those. So when I asked what x2 was, it came to be in terms of theta, cotangent. And so when my theta is small, when my point moves towards my origin, so I should be moving out to infinity. And that is indeed is what the cotangent does. Cotangent at 0 is infinite. Let's do the same thing, but for y. So y1 on r1 picks out the vertical component, sort of works like a sine, and then I'm multiplying it by the radius of the inverted point. And when I ask it to do that, it came out to 1/2. So back here, this point here is, the height of it is, from this origin, is 1/2. And I just get this 1/2 horizontal line. So the inversion of this arc is indeed just the horizontal line here and a horizontal line. So then I asked if, if that's the inversion, if that horizontal line on the outside of the circle is the inversion of this circle on the inside, then I sort of, in some sense, the inverse of the inverse or the converse of the inverse or something. I took what is what's if I took a chord here and asked what it was, what its mapped onto in this inversion process, and it was just the rest of this circle. And then I decided to do sort of a generic horizontal chord. Okay, so I wanted to see that. So that circle in particular, that chord becomes the rest of the circle, and that's a sort of a special circle here, and then it's a circle of the same radius as the original circle. But I decided to go more general and just take any horizontal chord and see what it mapped onto. So I stayed over here in Mathematica and I chose a y. So this is y of 0.2. It's no special value. You know, the special value we just played with was a half. This is no special value. Okay. But if I have, I want to go, so I'm making a table here. I'm working with a unit square. I'm going from x's, this 1 minus y squared. That's the x, within the circle. That's the y. That's the value of x that can be at this y. So I'm finding, like, on a circle, if I'm at a particular y, I'm going from this x to this x. So that's what's here. I'm going from minus the square root of 1 minus y to plus 1 square root of y, and I'm going up by 1/100. And then I am grabbing here, I'm making a table, I'm generating a list of x squared plus y squared is the r, and that's inside. And so x, and then I want the square root of that. So I want x on the square root of x squared plus y squared. That serves like a cosine. It grabs my horizontal component. And then I multiply that by the inverted radius, but that's just another square root of x squared plus y squared in the denominator. So it ended up to be overall x divided by x squared plus y squared. One of these, they're sort of, think of this as the square root squared. One of them is the x over that, sort of giving me the horizontal component, and the other one is the inverted radius of this circle inversion. So I'm just generating all that. So I'm calling this, I had a chord, which was just horizontal with this y of 0.2, and then I am taking my procedure to invert the chord. And that just gives me a big long list of numbers. And then I plotted it, and I called it CIP, the chord inverted plot or something. Just give it some name. It's easy for me to put things together if I give them names. So I had a list of x and y values, and so now I am plotting it. There we go. Now it looks indeed like a circle. Well, it looks like a little bit like an ellipse because it got a little bit of squash, but it is a circle. And Mathematica allows me to just define a circle. And the circle goes up to the reciprocal, the point here that was sort of like 0.2 gets mapped onto 1 over 0.2. So that was the 5. And then this is a radius, this is a circle, this is what we were seeing before, that the straight lines sort of have infinite radius, and then their inverses are circles that that touch the origin of the circle of inversion. So if I finish this chord, I expect this inverted chord, I expect this circle to go through 0. So that's just what I want to test here. So I played the game to do all the chord inversion. But now I'm taking a circle, and I just sort of argued that if my chord was at 0.2, then this is at 1 on 0.2, but the radius of the circle and the center of the circle are at half of that. So I've made a circle here. The x is 0. The vertical position of it is 1 over 2y, and the radius is 1 over 2y. So I made that, define that circle, and then I use this graphics method to draw it. And there we go. Now, it didn't give me a coordinate system, but there's sort of one, there is indeed one implied. And then if I bring them together with show, we see here that the blue, all these blue dots, that is my inverted chord, and the black is my circle. And you see it's just that little bit more. Okay. So that was some fun, just confirming this idea that chords, if you have a semicircle that goes through the origin, then its inverse is this parallel line. And then if you take the rest of that line, the chord, and you do its reciprocal, then you pretty much end up with a circle that goes through the origin, or would go through the origin. So you end up with the circle that outside of the circle, the inverted chord is the circle that if you extended it would go through the origin. Okay, so then I moved it back over to SVG, and I made this. Let me comment the last part out. So I just made a sequence of lines. These are chords. I don't quite have like the equator here. I just have a sequence of lines. So I decided this right now, I'm showing you, I guess it's 25. I'm going just a sequence of lines where I'm changing the y. So I divided the radius up, and I sort of lines of latitude, if you will. That's those red lines. And then I am believing what I had figured out over in Wolfram-Cloud Mathematica, that the relationship between those inversions and the arcs. And so then I was drawing down here, I'm making the paths in SVG. So you say where you're going to start. I'm starting. I determine a y. I have an r. It's not 1 because I have to give it some size to be able to draw it over here in SVG. But I have some r, then I divvy up, and I have some y as some fraction of the r. I figured out the corresponding x, and I'm making, here I make my lines that go from negative x to positive x for that y. And then down here, I start at the same place, M is the center. It's not 0 in an image. So I have this parameter M, which is my center. So I'm going from minus x, y to positive x, y. So that's the beginning of my arc, and that's the ending of my arc. And I'm making arcs again, which are my radius squared divided by 2y. And when you're making arcs in SVG, you have first you have this M, the starting point. Then when you define the arc, it's really an ellipse. So we're doing circles. So there are two radii that are both the same. And then you have these parameters over here. And one parameter is the rotation, but one for a circle doesn't make sense to do any rotation. And we had things that were sort of nice and horizontal and vertical anyway. But there are these so there's the radius, there's the A, there's the two radii that are the same because it's a circle. There's a rotation that's going to be for us 0. And then there's this large arc flag and the sweep flag. And this determines these sort of things. Are you taking, when you have 2 points and you're saying they're on the arc, do you want a small part of an arc? Do you want a big part of an arc? And so on. And I end up using, so each one of these is sort of 0 and 1. And to get the picture that I wanted here that sort of made sense, I needed to switch at some point. And I really sort of did it just by playing around, but the switching point would seem to be the square root of 1/2. And if I were thinking of angles, I'm comparing y and r. If I'm thinking of the corresponding angle, that would be sort of a 45-degree angle. So I had to switch these parameters. Again, the large arc flag and the sweep flag, I had to change them. I was changing the at sort of 45. And I made them different colors so you could see where I was making that change. So sort of from the center of the circle at a 45-degree angle, you can sort of see that seems to be roughly 45 degrees. I'm switching from the orange to the green to get these arcs. All right. And then I decided then I also wanted to sort of get the continuation of these arcs to sort of finish off the circle. And so that would be, these are the circle inverses of these horizontal lines. If I extended those horizontal lines to outside the circle, then what I'm going to find next is sort of the inverse of those. And that's what I had commented out, and now I'm going to bring in and now I have these. So all these circles are that the sort of outer, that green is continued by the magenta, the orange is continued by the blue. They all have a point, which is the origin of the circle of inversion, the original circle. And this is just it's the same radii, the same points, and it was just these other parameters. So it was like a good exercise in SVG arc making because it made me use all 4 sort of states, 0, 0, 0, 1, 1, 0, 1, 1. So it gave me sort of all 4 states of those parameters to get all the circles I wanted. So that's what I wanted to show you, just some playing around with circle inversion. Chords map onto circles, circles map onto chords, and chords need to be the circle needs to have some infinity, like that has an infinite radius. A chord has sort of an infinite radius, and that gets in the sort of inversion mapping that ends up corresponding to circles in inverted circles that touch this origin. All right, that's all I wanted to do on this one. Thanks for your attention.